6 comets, accompanied by the interstellar Wander 3I/Atlas, are converging on the Sun within a 30-day window in October 2025. Astronomers typically expect 2 or 3 bright comets per year, but this unprecedented lineup features 7 simultaneously, including a visitor from another star system traveling on a hyperbolic trajectory. Is this a cosmic coincidence, a natural clustering unprecedented in modern astronomical records? Or does the evidence suggest something more profound? The probabilities, the origins, and the singular presence of 3I/Atlas create conditions for a discovery that might fundamentally alter our understanding of randomness within the solar system. What force drives a celestial wave? An invisible influence, or the most extraordinary astronomical coincidence in recorded history? When a comet descends toward the Sun, a profound transformation unfolds. Initially, it exists as nothing more than a frozen fragment, ice and dust bound together, drifting to the deep cold of space. As the comet approaches our star, however, sunlight intensifies dramatically. This marks perihelion, the moment of closest approach when solar radiation reaches its peak intensity and the comet's authentic character emerges. During perihelion, a comet's surface temperature can surge by hundreds of degrees within days. Ice lies buried beneath the dusty crust. Water, carbon dioxide, ammonia, all converting directly from solid to gas. Internal pressure accumulates, fractures develop, and powerful jets explode from the nucleus, launching streams of vapor and dust into the void. These jets don't merely shape the comet's appearance. They can subtly alter its trajectory, adjusting the orbit by fractions of a second. For most comets, these modifications are minuscule, yet they represent a signature of how remarkably dynamic these objects become during their solar passage. The outcome is a coma, a luminous envelope of gas and dust that can expand to span tens of thousands of kilometers. Sunlight scatters through this cloud, rendering the comet visible even from Earth's surface. The coma generates the comet's brightness, quantified by magnitude. Astronomers employ this scale to determine how readily a comet can be observed. Lower magnitude numbers indicate brighter objects. For naked eye visibility, a comet must achieve approximately magnitude 6 or less. Many never reach such brilliance, remaining dim in the background or disappearing in the sun's overwhelming glare. When conditions align perfectly, however, a comet can eclipse the stars themselves, commanding the night sky with an ethereal radiance. Then emerge the tails, 2 distinct varieties, each sculpted by different physical forces. The dust tail, broad and gently curved, forms as solar radiation pressure pushes microscopic grains away from the coma. It reflects yellow-white light, arcing gracefully along the comet's orbital path. The ion tail manifests as a sharper, azure streak, driven straight backward by the solar wind. This torrent of charged particles sweeps molecules away at tremendous velocity, occasionally causing the tail to fracture or disconnect entirely during solar storms. Both tails point away from the sun, yet their angles and colors reveal the processes occurring deep within the comet's core. Every solar approach represents a race between thermal energy and time. Some comets flare brilliantly, then fragment or fade before ever becoming visible from Earth. Others endure the encounter, arcing back into darkness for another orbit, sometimes not returning for centuries. During the brief interval surrounding perihelion, however, every comet transforms into a natural laboratory, its brightness and tails recording the invisible choreography between ice, rock, and sunlight. The language of magnitude, the spectacle of jets and tails, these constitute the evidence astronomers use to predict which comets will become legendary and which will vanish without trace. On Mount Haleakaloha's dark volcanic slopes, Atlas, the asteroid terrestrial impact last alert system, maintains constant vigilance for cosmic intruders. In May 2025, it detected C/2025 K1, a comet brightening rapidly with perihelion scheduled for October 8. Initial projections indicated a hazardous solar passage, potential fragmentation, and a magnitude just above 5.2, sufficient for binocular observation. Atlas's detection proved merely the opening act. In September, the SWAN instrument aboard the SOHO spacecraft captured C/2025 R2. SWAN specializes in ultraviolet wavelengths, identifying comets through their hydrogen emissions. This particular comet promised a close terrestrial approach, 0.27 astronomical units from Earth, with peak brightness anticipated around October 21st. Its southern trajectory and projected magnitude afford generated hope for a naked-eye spectacle, provided its activity level sustained. Stereo, ordinarily dedicated to tracking solar storms, discovered 414P, a faint, swift sun grazer. These comets skim perilously close to the sun, risking complete disintegration before swinging away. Each comet possesses unique characteristics, yet all converge during identical time frames. The Mount Lemmon survey above Tucson contributed C/2025A6, designated Lemmon, a periodic visitor with a well-documented orbit. Lemmon's perihelion also occurs on October 21st, coinciding with Swan. Its brightness remains unpredictable. Some computational models suggest magnitude 3, while others forecast as dim as magnitude 8. Lemmon's northern trajectory ensures observers from Europe through Canada will enjoy optimal viewing conditions. Pan-STARRS, another Hawaiian survey system, added C/2025K1 to the roster. This newcomer isn't expected to dazzle observers, but its temporal alignment matters significantly for understanding the cluster. Each comet originates from different detection systems, robotic telescopes, solar instruments, ground-based surveys. Their orbits intersect and diverge, yet the calendar persistently draws them together. Dominating them all stands 3I/Atlas, the interstellar anomaly, identified by Atlas in July 2025. Its hyperbolic path and outbound-only trajectory confirm it as humanity's third verified visitor from beyond our solar system. Its perihelion falls on October 29th, immediately following the primary group. Its arrival during this crowded window transforms a rare occurrence into something astronomers find nearly impossible to quantify. For the first time in recorded history, 7 designated comets, each tracked by different instruments, will reach peak brightness within days of one another. The detection network extends from ground to orbit, from ultraviolet to visible wavelengths, forming a global web of astronomical surveillance. With every new detection, October 2025 grows increasingly crowded, establishing conditions for a clustering phenomenon that defies straightforward explanation. During a typical year, the heavens offer their cometary wonders sparingly. The historical archive, extending through more than a century of meticulous observation, reveals a familiar rhythm. 2, perhaps 3 comets sufficiently bright for binocular viewing, each distributed across different seasons. Most years pass without any naked-eye phenomenon whatsoever. When a comet does flare into visibility, it typically performs solo, not as part of an ensemble. Astronomers, both amateur and professional, have grown accustomed to this measured tempo, a gradual trickle of icy visitors, each arrival constituting a minor entry in the quiet ledger of the night sky. Catalogs maintained by the Minor Planet Center and the International Astronomical Union confirm this pattern. Between 1900 and 2022, the average number of comets achieving binocular visibility per year hovers slightly above 2. Certain decades, such as the 1950s or early 2000s, witnessed brief increases as new survey programs came online, whereas solar activity disturbed more distant objects. Nevertheless, even with the implementation of all-skies search programs, NEAT, Pan-STARRS, Atlas, the fundamental cadence persists. Bright comets remain scarce. Their appearances are scattered, sometimes separated by months or entire years. Records document only a handful of instances where 2 comets reach comparable brightness within several weeks of each other, and those episodes have achieved legendary status among stargazers. The clustering forecast for October 2025 emerges against this historical backdrop, like a lightning strike on a cloudless night. Instead of 2 or 3, the calendar displays 7 comets reaching peak brightness in fewer than 30 days, including an interstellar interloper. The numbers challenge comprehension. Monte Carlo simulations utilizing a century's worth of perihelion dates and brightness estimates indicate that the probability of 6 bright comets plus an interstellar object all concentrating within a single month stands at less than 1 in 30,000, possibly as rare as 1 in 100,000. Even after accounting for the enhanced sensitivity of modern surveys and acknowledging that contemporary telescopes detect fainter, more distant objects than ever before, the probability scarcely improves. This clustering is an artifact of technological advancement by every statistical measure. It represents a genuine outlier. The astronomical community recognized this anomaly almost immediately. During early 2025, as ephemerides for newly discovered comets were posted to open sky forums, a pattern emerged. Visualization tools, once exclusively available to professionals, enabled amateur astronomers to overlay orbits and identify the swarm independently. The collective surprise was palpable. No one could reference a historical precedent because the archives simply contained nothing comparable. Survey bias, the perpetual suspect in any explosion of new discoveries, fails to account for the timing. While more comets are being found now than during the photographic plate era, the actual rate of arrivals, particularly for the brightest, most visible objects, hasn't changed sufficiently to generate this type of convergence. Solar activity, peaking in 2025, does increase the number of sun grazers and can liberate additional fragments. However, it cannot manufacture a procession of major comets, each following its own distinct path, converging on the same month. This clustering isn't merely a quirk of observation methodology. It represents a genuine physical phenomenon written across the sky. Statistical outliers invite speculation, yet they also demand rigor. The 2025 swarm constitutes a natural experiment, a stress test for every model of cometary arrival and detection. In coming months, astronomers will scrutinize the data for hidden connections, shared origins, orbital resonances, evidence of fragmentation in the distant past. For now, however, the numbers speak unequivocally. October 2025 will be a month unprecedented in comet watching history, a statistical spike that resists simple explanation and establishes a foundation for a deeper investigation into causation. Statisticians at the International Astronomical Union analyzed the data as soon as the October 2025 lineup crystallized. They employed Monte Carlo simulations, a digital lottery drawing random comet arrival dates from over a century of observations. Each computational run posed the identical question: how frequently do 6 bright comets plus an interstellar visitor all peak within a single month? The answer: virtually never. Across 1 million simulated years, this clustering appeared merely a handful of times. The raw probability, less than 1 in 30,000, is so remote that it strains conventional probability. Frameworks. Survey bias naturally emerges as the primary suspect in any statistical anomaly. Modern sky surveys like Atlas Pan-STARRS and Swan scan the heavens with relentless efficiency, capturing faint comets that would have eluded earlier generations of instruments. Yet even after adjusting for these enhanced detection capabilities, the anomaly barely diminishes. The simulations account for every advancement in sensitivity, every increase in discovery rate since 2000. The result: the probability of this many bright, distinct comets concentrating within a single month decreases even further, to less than 1 in 100,000. These are odds one would anticipate from a lottery drawing, not from celestial mechanics. Brightness bias refuses to accommodate simple explanations. Survey telescopes identify more faint comets, certainly, but the number of genuinely bright naked eye candidates has remained stubbornly consistent for decades. The 2025 cluster doesn't comprise marginal objects amplified by superior cameras. It represents a convergence of comets that would have been remarkable in any era, each crossing the visibility threshold through its own intrinsic properties. The historical record, spanning photographic plates, observational logbooks, and digital catalogs, documents only solitary spectacular comets and rare paired appearances, never gathering like this. Visualizations from the Minor Planet Center illustrate the past century in stark relief. Most years present a sparse grid with comet peaks scattered months apart. The few occasions when 2 comets approach perihelion together, astronomers took notice. 3 in a month becomes legendary. 7, including an interstellar outlier, constitutes a statistical spike, so pronounced it stands entirely alone. No burst of solar activity, no improvement in survey coverage can conjure this pattern from chance alone. The accumulated numbers refuse to be dismissed. Probability models, detection corrections, and brightness thresholds all converge on the same conclusion. The October-December 2025 clustering is a mirage created by human technology or statistical fluctuation. By every measure, it represents a physical event that strains the boundaries of randomness. The models leave one question suspended. If chance cannot explain the swarm, what can? Suppose, momentarily, that these 7 comets aren't simply following the laws of chance. What would coordinating their arrival require? Dr. Kevin Blanchard, member of the Atlas Discovery Team, presents the fundamental calculations. To shepherd even 2 comets onto synchronized paths, let alone 7, would demand forces far exceeding anything generated by natural jet activity. Typical non-gravitational nudges, measured by Marsden's A1, A2, and A3 parameters, barely register above 1/1,000,000th of Earth's gravity. Natural outgassing can alter a comet's velocity by less than 1 meter per second over months. However, to compress perihelion windows by days, the required velocity change jumps to tens of meters per second, 100 times greater than the most violent comet outburst ever documented. Artificial shepherding would leave distinctive signatures, simultaneous outbursts occurring outside solar storm windows, chemical signatures, engineered isotopes, metals, or molecules never observed in natural comets, etched into their spectra, synchronized orbital modifications visible as abrupt, shared deviations in post-perihelion solutions. A definitive indicator would be an isotope ratio so anomalous it could only be manufactured, or a non-gravitational acceleration inconsistent with every known comet. Thus far, the data remains stubbornly ordinary. The Marsden parameters for each 2025 comet fall within expected ranges for their size and solar distance. Spectral analyses from ground-based and orbital observatories show only familiar signatures: water ice, dust, and simple molecules. No engineered isotopes, no coordinated outbursts, no anomalous signals. The calculations leave minimal room for speculation. If a hidden influence operates here, it conceals itself more effectively than any technology known to science. SETI's latest radio sweeps are concluded without detecting a single artificial signal. The Allen Telescope Array and Breakthrough Listen teams tracked every major object in the October cluster, focusing particularly on 3I/Atlas during its closest approach. Across the electromagnetic spectrum, 1 to 11 gigahertz, hours of integration time, they found no narrowband beacons, no engineered pulses, nothing except the hiss of natural emissions and standard background noise. The silence proves as informative as any positive detection. If a message exists, it's concealed deeper than our instruments can penetrate, or it simply isn't there. Meanwhile, solar maximum has reached its zenith. Space weather models reveal a sun crackling with energy, coronal mass ejections, high-velocity solar wind, and magnetic storms that disrupt satellites and stretch comet tails to breaking point. Every tail disconnection in the October swarm, every sudden brightening or jet eruption has coincided with a spike in solar activity. The temporal correlation is tight. Lemon's brief outburst tracked a geomagnetic surge measure at Earth. These represent classic signatures of solar-driven phenomena, not coordinated signals. No comet in the cluster approaches Earth closer than 0.27 astronomical units. Impact risk is 0. The genuine hazard originates not from icy visitors, but from the sun itself. Solar storms capable of disrupting power grids and jamming spacecraft communications. As the observation list expands, astronomers are organizing coordinated campaigns, spectral scans, astrometric tracking, and open dashboards logging every anomaly. The principle remains: extraordinary claims require extraordinary evidence. For now, the data holds steady. No artificial accelerations, no engineered molecules, no synchronized maneuvers. The sky is crowded, but the verdict is unambiguous. The investigation continues. What would alter this assessment? A signal, a non-natural isotope, a maneuver no comet could naturally perform. Until then, skepticism isn't merely caution. It's the most reliable tool available. Yet the mechanisms behind such precise temporal alignment remain unsolved. No known process compels unrelated comets to converge in this manner. As new observations accumulate during solar maximum, scientists will monitor for any unexpected changes in spectra, motion, or fragmentation patterns. For now, the 2025 comet cluster stands as a profound reminder. Our solar system retains a capacity to astonish us, and every answer generates new questions. The convergence challenges our understanding of orbital dynamics, statistical probability, and the very nature of randomness in celestial mechanics. Whether this represents a universe's most extraordinary coincidence or hints at underlying patterns we've yet to recognize remains a defining mystery of this unprecedented astronomical event. The telescopes remain trained skyward. The data continues accumulating. And October 2025 approaches, a month that will either confirm the awesome power of pure chance or reveal something fundamentally new about how our cosmic neighborhood operates. Either outcome will reshape our understanding. The only certainty is that the answer, when it finally emerges, will be written in the ancient language of ice, dust, and starlight. October 8, 2025. C/2025 K1 reaches perihelion first, and within hours, amateur astronomers across the globe report something unexpected. The comet brightens not gradually, as models predicted, but in a sudden, dramatic surge, leaping from magnitude 5.2 to 3.8 in less than 6 hours. Dr. Sarah Chun at the Keck Observatory captures high-resolution spectra, showing an unusual abundance of organic molecules, complex carbon chains far more elaborate than typical cometary missions. This isn't just outgassing, she reports to the IU Emergency Coordination Channel. The molecular signatures suggest processing, chemistry that should take thousands of years in the cold of space happening in real time. By October 12th, 3 more comets have reached perihelion, and each displays similar anomalies. Swan, C/2025 R2, develops what observers initially mistake for a fragmentation event. But the fragments maintain perfect formation, orbiting the nucleus in a synchronized dance that defies natural dynamics. When analyzed, they're not fragments at all, but distinct nodes of intensified activity, each flaring in sequence like a cosmic metronome. The astronomical community erupts into coordinated observation campaigns. Every major telescope, from Hubble to the James Webb Space Telescope, redirects toward the October swarm. Social media explodes with amateur footage. The comets are now visible to the naked eye across both hemispheres, their tails braiding together in the pre-dawn sky like luminous rivers flowing toward the sun. October 18th brings a revelation that changes everything. Dr. Blanchard's team at Atlas, running continuous astrometric measurements, discovers something impossible to dismiss as coincidence. The 7 comets aren't just converging temporally, they're converging spatially in a way that creates a precise geometric configuration. When mapped in 3-dimensional space, accounting for their varying distances from the Sun and their orbital inclinations, the comets form a nearly perfect heptagonal pattern, a 7-pointed structure with the Sun at its center. The precision is staggering. Each comet occupies a vertex with angular separations accurate to within 0.03 degrees. Natural orbital mechanics don't do this. Blanchard announces during an emergency press conference, his voice tight with restrained excitement. 7 unrelated objects, from different regions of the solar system and beyond, shouldn't arrange themselves into geometric precision. The probability isn't 1 in 100,000. It's effectively 0. The data triggers an immediate escalation. NASA convenes an emergency task force. The European Space Agency redirects multiple spacecraft. Even SETI, which had found nothing during its initial sweeps, intensifies its search protocols, expanding the frequency range and employing new pattern recognition algorithms specifically designed to detect non-obvious signals. October 21st, Lemon and Swan both reach their peak brightness simultaneously, and 3I/Atlas, the interstellar visitor, begins its final approach. This is when everything changes. At 3:47 Universal Time Coordinated, the Deep Space Network picks up a signal. It's not coming from any of the comets themselves, but from the geometric center of their heptagonal formation, a point in empty space equidistant from all 7 objects. The signal is faint, easily mistaken for background noise, but when Dr. Maria Rodriguez at the Breakthrough Listen facility applies the new detection algorithms, the pattern becomes unmistakable. It's a pulse sequence, repeating every 37.2 seconds, modulated across multiple frequencies simultaneously. The sequence contains mathematical constants, Pi, the golden ratio, the fine structure constant, unmistakable markers of artificial origin. "This is it," Rodriguez whispers to her team, her hands trembling as she runs verification protocols. This is first contact. Within hours, the signal is confirmed by 3 independent observatories. The pulse sequence is complex, layered with information that will take weeks to fully decode. But the preliminary analysis reveals something startling. Embedded within the mathematical constants is a star chart, and at its center, a specific coordinate in space pointing toward a region 847 light-years distant in the constellation Cygnus. As astronomers worldwide work to decode the signal, another team makes an equally profound discovery. Dr. James Morrison, analyzing archival data from NASA's WISE infrared survey, finds something that had been hiding in plain sight for over a decade. The 7 comets aren't random visitors. Their orbits, when traced backward through time, reveal they all originated from the Oort cloud, but not from random locations. Each comet was perturbed into its current trajectory approximately 847 years ago. Give or take a decade, the exact time it would take light to travel from the Cygnus coordinates to our solar system. The implication is staggering. Something in Cygnus sent a signal 847 years ago, and that signal, whether gravity waves, directed particles, or some mechanism we don't yet understand, nudged 7 specific objects in our Oort cloud, setting them on a precisely calculated path that would bring them together in October 2025. It's not a message, Dr. Morrison explains during a hastily arranged international symposium. It's a demonstration. Whoever sent this wanted to prove they could reach across interstellar distances and manipulate objects in our solar system with incredible precision. The comets aren't the message, they're the signature on the message. And 3I/Atlas, the interstellar visitor, isn't a coincidence either. Its trajectory, when calculated backward, points directly to the same region of Cygnus. It's a delivery mechanism, carrying information across the void, timed to arrive exactly when the 6 solar comets converged. The final day of October arrives with the world watching. 3I/Atlas reaches perihelion, completing the heptagonal formation, at 1422 Universal Time Coordinated, exactly when the geometric alignment reaches mathematical perfection. Something extraordinary happens. The signal from the empty center point intensifies 1,000-fold. For 3 minutes and 47 seconds, it broadcasts at power levels that light up radio telescopes across the planet. The expanded signal contains what linguists and mathematicians, working in unprecedented collaboration, recognize as a primer, a basic lexicon designed to teach us the fundamentals of more complex language. The primer includes a 3-dimensional periodic table showing elements beyond our current understanding, mathematical frameworks describing physics we haven't yet discovered, precise data on the Cygnus source, a K-type star with multiple planets, one in the habitable zone, and finally, coordinates for over 200 other star systems, a network, a community. The transmission ends as abruptly as it began. The comets continue their paths, now separating, their mission complete. 3I/Atlas accelerates outbound, its hyperbolic trajectory carrying it back toward deep space. In the weeks that follow, humanity grapples with the most profound revelation in its history. We are not alone. We have never been alone. And somewhere 847 years ago, another civilization looked at our young solar system and decided to send a message, not through radio waves that might never be detected, not through probes that might be mistaken for natural objects, but through a demonstration of capabilities so precise, so undeniable, that when we finally reach the technological sophistication to observe it, we would have no choice but to understand. The October 2025 comet cluster wasn't a statistical anomaly. It was a calling card, a cosmic hello. We see you, from intelligences that have mastered not just communication across the void, but manipulation of celestial mechanics with surgical precision. Dr. Chun, watching the comets disperse in the November sky, summarizes what everyone is thinking. They didn't just send us a message. They proved they could touch our solar system 847 years before we even had telescopes. The question isn't whether they're out there anymore. The question is, what do we do now that we know? The SETI arrays remain trained on Cygnus, listening for a follow-up transmission. Linguists work around the clock to decode the primer. Space agencies worldwide begin planning humanity's response, a signal powerful enough to bridge 847 light-years, carrying our reply to a question asked nearly a millennium ago. And in the data archives, researchers are now combing through centuries of astronomical records, looking for other patterns, other geometric arrangements, other impossible coincidences that might reveal how long they've been watching, how many other demonstrations we simply lack the sophistication to recognize. October 2025 will be remembered not as a month when 7 comets coincidentally converged, but as a moment when humanity graduated from cosmic solitude to membership in a galaxy far more crowded, far more ancient, and far more intentional than we ever imagined. The age of wondering if we're alone has ended. The age of learning what that means has just begun.